My name is Kai, and I'm representing Meanwhile, and we are a standard power supply manufacturer. And I'm here today to talk to you guys about powering success. So every electronics, there's any electricity, anything that needs power, there is a power supply. So today I want to go over the reliable power supply implementations and the key considerations in successfully and reliably using those power supplies. All right, so here's today's agenda. So first I'll give you guys a brief introduction on why we're talking about power supplies. And I will go over the key considerations from electrical to thermal to control perspectives. And then finally, we have some solutions to share with you guys. So the importance of choosing the right power supply, the reason why I'm here is to tell you guys that, right? And the main reason is because you can think of the power supply as the heart of the machinery. Without the power supply, without a good power supply, the machinery cannot reliably run. So for the power supply selections and the design choices, there are many key considerations. So from the electrical perspective, we can look at the input and output, and then also the efficiency, the electromagnetic compatibility. All of those are very key considerations for electrical. And then in terms of thermal, there's also the ambient temperature of the end customer device, the operating environment, and then the over temperature protection for the devices and for the power supplies. You don't want the power supply to overheat in the application. And then finally, the installation as well, because that's very important for the thermal. And then in terms of controls, you want to be able to control your devices. And the easiest way to do that, the first point of access, the power supply. So for things like remote on-off, that can be easily achieved via the power supply. And then the output of the power supply also needs to be adjusted in some applications to be able to provide a flexible power supply voltage for various flexible applications. And then finally, remote monitoring is the more advanced applications for power supplies. If you are able to monitor the cameras, the devices, the sensors, why can't you monitor the power supplies? Getting information from the power supplies is very beneficial for various applications. So we'll delve into that a little bit in the later. All right, and then for the application scope for our power supplies, so we cover automation, industrial. That's what Meanwhile is most well known for. But we also have a large selection of medical LED driver products, and then we're also getting into green energy for energy storage applications, EV charging related applications. And we also have products that's catered towards IT or telecom applications. And here are a very brief overview of the different types of power supplies. So on the left, top left, we have the most generic enclosed power supply. And it's basically a power supply with a metal enclosure, and we also call this a chassis mount power supply. So the way the customers use this is usually mounted inside of a bigger system enclosure or in a control panel. And then the power supply's input and outputs are terminal blocks. So it's hardwired to the power supplies and for factory installation. And we also have LED power supplies, which are typically input and output wires with IP-rated design. So, and then the next is DIN rail. And that's what a lot of automation applications use, because DIN rails are easily installed into the control cabinets. They're very easy to use, just pop in and snap on, and then you can wire them in the field as well with the screw terminals. So DIN rails are very popular for automation. And then next we have open frame. So open frame is just the PCB of the power supply. So it's very similar to enclosed type, but without the metal enclosure or the enclosure around it. And the reason customers may want to may use the open frame is for cost saving and for downsizing for the application. So for the enclosed power supplies, typically the power supply is packaged, especially the higher power units are packaged with fans or other cooling mechanisms. But for lower power supplies, lower power products, the open frame will suffice. And for the customer, if your applications, they have the fans built inside, they can already provide the sufficient cooling without the increased space and size of the enclosure. And the next, we have the desktop. Desktop mount is very popular for chargers, adapters, and for, say, your phone, your laptop chargers. Those are a type of adapters. And they're very, very cost-effective for customer applications that want to just certify their products with a DC input. They don't want to worry about AC, so they just certify their products with a 24-volt DC, and then can get a UL-listed adapter to go along with the products, and they can market worldwide if the adapter has global certifications. And we also have some special KNX-based products, which is a automation control protocol for Europe. And on the right side, we have DC-DC converters, which is mainly used for board mounting or inside enclosure installation. And then we have battery chargers, DC-AC inverters as well, so I won't go into much detail about those. But I think we mainly want to focus on the DIN rail product type because that's more popular for the automation industry. So that was a brief overview on the types of power supplies there are. So let's talk about the electrical considerations. So the first thing is the power ratings and derating. So in choosing the right power supply, the first thing you want to nail down is, of course, the power rating. You want to know what's the input voltage for your device that you want to build, and then what's the output voltage for the power supply that your device needs. So it can be 24-volt DC, 48-volt DC, and we are seeing also more and more higher voltage applications nowadays. So here's a snippet. It may be a little bit small, but it's a snippet of one of our product specs. And we will tell you the input voltage, the output current. So these are very important values in determining how big your power supply needs to be and what size your power supply needs to be. And it's also very important to consider derating for your application. So general recommendation from the power supply manufacturers, of course, we recommend to leave at least 30% margin for power supplies. So if your application requires 100 watts, it's generally best to go with a 130 watts of power supply or higher so that the power supply has long lifetime longevity and also reliability is ensured. And then additional power margin may be needed if the application is also used in very extreme temperatures or very different input conditions. So at the bottom right corner here, we have a derating curve versus the temperature. So you can see that for our power supplies, typically we rate it up to full load, up to 50 degrees Celsius. However, if your application requires the temperature to go higher, you're in a very humid, very hot factory or plant, you may need to go to 70 degrees Celsius or even higher. So to push the power supply to those higher temperatures, you need to be able to derate the output power accordingly. And for a lot of the products, typically the maximum derated temperature, usually 70 degrees Celsius or 85 degrees Celsius, and the manufacturer will specify what's the maximum load. So for this specific example, you will have about 50% of the rated power left if you're using at 70 degrees Celsius versus you were using at 50 degrees Celsius. And then another consideration for derating may be the input voltage. Some products have input voltage derating as well, so you may want to pay attention to those as well when you're choosing a power supply, especially for higher voltage, higher wattage applications. And it's some of the limitations may be due to the heat dissipation because the power supply is running at higher current when it's had a lower input voltage. But some consideration may be just because of the power rating limitations, because you can only access so much current from a 115-volt AC line. So talk about electrical considerations, and we're at the ATX automation show, right? So there are a lot of peak power related applications from motors or solenoid valves and other inductive or capacitive loads that draw a lot of peak current during the operation. And in this graph here, for example, the steady state current is only about 10 amps. However, when the motors turn the loads, like it's a conveyor belt system in a factory, when it's carrying all the load may get up to, the current may need to go up to as high as 54 amps. So that was captured during the actual operation of the conveyor belt. So traditionally, if a customer wants to power this system reliably, they would need to go for a power supply that is able to provide the needed voltage and then be able to provide the 54 amps current at least, so that the system does not shut down or does not have longevity issues. However, there are recent years, and including meanwhile, we've started to develop power supplies that are specially catered towards peak power applications. So we can have power supplies that's rated for 300 watts, that's able to sustain up to 1,000 watts of peak power. And that's able to help the sizing and selection of the power supply So you don't need to size a 54 amp power supply just for a 10 amp steady state current application. And at the bottom is just a graph demonstrating the operating region of a 600 watt power supply with a 350% peak power capability. So you can see that it's able to get up to towards of 1,800 watts or even more peak power. And of course, the duration and the power that you can get out of it depends on the duty cycle of the peak power duration. So if your peak power is only 700 watts, the power supply will be able to sustain that for a very much longer time than if your peak power is at 1,800 watts. So if it's at 1,800 watts, the duty cycle for that peak power may only sustain up to 5%. And here's an actual example of where a peak power supply was able to simplify a pinball machine design. And this is also applicable to all these automation equipment that uses solenoid valves or motors. So this specific example, the customer was using a solenoid valve. And so their old power supply, they were using a 500 watt power supply, which had a nominal output rating of 500 watts. And the peak power without shutting down, without the OLP shutting down, was 580 watts. That's the overload protection setting point, right? And the customer had to add a capacitor, bulk capacitor board to the output of the power supply in order to sustain the solenoid valve's peak current draw. At the instantaneous moment the solenoid valve kicks in the pinball machine, it needs that instantaneous power. And that was costly to the customer as well, and they need to add these extra boards, extra design, engineering time and production time, as well as the bulk capacitors. They are not cheap, right? And later on, once we released the peak power products, customer was able to evaluate and swap in a 300 watt power supply to replace the 500 watt and completely eliminate the bulk capacitors that's needed for the solenoid valves. So just in comparison, the 300 watt power supply with peak power, the peak power output with OLP is rated up to 1,050 watts. And in terms of sizing, because it is technically a 300 watt power supply, it is much smaller in comparison to the 500 watt power supply, and then the cost is much less as well. So just for the meanwhile's cost, right? So the cost is roughly about 18% lower than the 500 watt, and it has all the added features. And then the customer was also able to eliminate the need for the external capacitor boards. And another electrical consideration is the wiring and termination. So for wiring and termination, customers need to consider the steady state current. They typically size the wiring gauge, the wiring or the bus bar size based on the steady state current. However, a lot of the oftentimes overlooked consideration is the abnormal current. So if there's a short somewhere along the device or in the device that's not protected with a fuse or circuit breaker, and the wiring size is only according to the steady state current. The abnormal state current may be a short or in hazardous cases, it may be shorts across the AC line, right? So it may induce very high short circuit current, and that can have a fire hazard. So abnormal current also needs to be considered when the customer is sizing the power supply wiring. And a way to get around this is to add fuses and external protections on the wiring line in order to reduce the wiring cost to help downsize the wiring. And also, if the power supply and the load is very far distant apart, the line voltage drop needs to be considered as well. So line voltage drop can have a very adverse effect for long distance. Sometimes we've seen line voltage drops of 1 volt to 1.5 volt just for like a 24 volt power supply. So it can have very drastic difference at the output of the load versus the power supply's output. And then, so those are the key considerations. And here's a example of what we are able to do and what we've done for one of the customers in the past. This was a very difficult system to wire, and this was a 75 kilowatt system utilizing 6 racks of the meanwhile power solution racks. And then the input per phase was 130 amps. And then the output was 600 amps total. So the input we had to select if you see on the right side, a very large AC terminal block. And the internal wiring, we also had to size according to the 130 amps per phase. And then all of these, especially the DC lug part, was customized for the customer's requirements, where they wanted like two sets of bus bars that's able to sustain 600 amps each. And then they asked us to drill 3 holes on each of the bus bars as well, because they had 3 load devices that they wanted to wire it to. So they didn't have to mess around with the lugs and bus bars. So if you guys find it difficult to work with, especially the high power installations or integrations, you can always reach out to the manufacturers for the power supplies to ask for advice, or also help you with the integration of the wiring and the terminations. So next, let's move into thermal. So why is thermal management important? So general rule of thumb is that because nowadays we're all trying to get higher power, but we're also trying to downsize the products. We're adding more and more components to our devices, but we're also, pressed by the customer. They are limiting in space, or they don't want to have a lot of estate to run your equipment. So we're asking for higher power and lower size, which means that internal to the devices, the temperatures will go up as well. And the general rule of thumb is that the failure rate doubles for every 10 degrees Celsius rise in the temperature. So we want to have a very good power management, thermal management, in order to have a reliable power supply integration. And so next I'll go over a few of the cooling options available, and then the advantages and disadvantages of both. And then finally I'll summarize on what's the right solution for you, like what's the best selection for your equipment. So the first and most common is the forced air convection. We also call this the fan cooling. And the advantage for this is easy implementation, and it's very low cost. A lot of the high power enclosed power supplies, they come with built-in fans, and they're able to run. So those are all convection, forced air convection power supplies. And of course, the challenges is the airflow impedance. You cannot have the power supply in a very enclosed space, very tight space. You need to allow enough airflow, whether it's venting or internal airflow, for the power supply to be able to circulate the air effectively. And then there's also the consideration for noise. The fans may be very noise-inducing and very loud. And of course, fan failure. Fan failure is one of the highest failure rate components in a lot of the electronics. So by using fan, we have to consider the fan failure rate as well, which limits the lifetime for the power supply and the final products. And the next type of cooling option is the free air convection. So it's basically utilizing a conduction cooled to get the heat out of the components. And also, there's also designs that utilize enclosure surface for conduction cooling. And there are some thermodynamics formula for the convection and cooling. The heat dissipated is equal to the HA delta T. So the H is the material constant, and then the A is the surface area, and then the delta T is the temperature difference between the medium that you're trying to transfer heat to, and then the medium that the heat is generated from. And of course, the advantage for the free air convection is that the elimination of fan. So we get rid of the fan, we increase the reliability of the system and the power supplies. And the environmental protections as well for the fully potted especially. So we have designs that are fully sealed and fully potted, IP-rated power supplies that's able to withstand the weather, withstand the rain, and does not rely on any additional components for the free air convection. So the free air convection cooling will have a slight difference. You will see in the next slide that will talk about conduction cooled. They will be very similar, but free air convection means that you don't need to rely on any external cooling method. The power supply itself, if you see in the picture, already has the cooling fins and the heat sinks designed into its enclosure. And the challenge for using this type of power supply would be the weight and the cost. So this is typically the top of the line premium power supplies designed for ruggedized, outdoor, harsh environment applications. So the cost is very high. And since we are using potting compounds to get rid of the heat and to provide the environmental protection, sometimes these power supplies may also weigh 3-4 times more than another, like a forced air cooling power supply in the same power range. And next is the conduction cooling. So conduction cooling is also not using fans to cool, and it typically relies on a base plate or heat sink to extract the heat from the power supplies and the high heat components. So again, we're eliminating the fan, and it's lower cost in comparison to the fully potted premium free air convection models, and it is directed heat removal. That means the designer, the system designer, you have control on how you want the heat to be extracted from the system. So for the convection cooled and the forced air cooling, the fan circulation, if the airflow is internal, it's very hard to extract the heat from the internal of the system. But if it's in a conduction cooled design, if you have the heat sink that's mounted external to the device, or you can direct it via other means, then you can direct the heat away from the system and away from other heat-sensitive components that may be inside of your device. And the challenge, of course, is it requires an external heat sink. And this can typically be provided by the power supply manufacturer, or you can design your own or buy off-the-shelf heat sinks. And the next one, and the most advanced one, I want to say, would be the water cooling. And there are multiple approaches to the water cooling. So the first approach is a water-cooled heat sink. So this is still a similar concept than like the conduction cooled, where it is utilizing a heat sink to extract heat from the power supply. But we're using water and liquid cooling chillers to circulate the heat away from the heat sinks. So the advantage for this is the high heat flux density removal, which means we're able to support higher power designs and higher power density within the power supply and within the electronic devices. And it's able to generate a very high efficiency at very high power. So the water cooling applications are typically seen in higher power designs, factory level, food processing equipment, things like that. So that's the first approach. The second approach is water-cooled components. So the first one was water-cooled heat sink. The second one is water-cooled components. And so this is a more dangerous design for the power supply, because we're circulating water through the power supply, within the power supply, through the high heat components. This is more effective at extracting the heat. However, this also requires more design considerations when we're designing the power supply, and also for the users when they're using the power supply, to ensure there's no leaking or any hazards to the system, because we're delivering and converting high power, but we're also running water, which don't mix really well with electricity. And of course, the challenges is the complexity of the system. It requires the external chillers, and then the cost. So the cost for the power supply and the chillers are both additional costs to the system. So we see customers that utilize water cooling are typically customers that already have water chillers in their system. So a lot of the customers that use, say, laser diodes, diode lasers, that they already use the chillers to cool the laser heads, they would just need to route the water to the heat sinks or through the power supply. Okay. So which cooling method is the best for you, right? So I've listed a few criteria here. And so if you're looking for something that, if you're concerned about acoustic noise, you definitely want to go with free air convection or conduction cooled. And then if you're worried about component reliability in a very high efficiency, high reliability setting, water cooling is important because it keeps the components the coolest. And then for environmental protection, the free air convection cooled, because I mentioned earlier that we have designs that are fully potted and fully environmental proof. And for the cost, forced air convection, it is the most common, most easy to implement, and the lowest cost implementation. And then for the power level, if you want to really push the power level, you have a very high power density, very high power system, you want to utilize some form of water cooling to remove the heat. And in terms of the system size, conduction cooling is typically the best because your enclosure can act kind of as a heat sink in some of the cases if it's metal. And again, in terms of integration difficulty, if you just want to have a quick and easy power supply to power your system, forced air convection and free air convection are the easiest to work with. And here's a case sharing where a conduction-cooled power supply was used on board of a warehouse robot as an onboard charger. So in this specific case, the fanless power supply was chosen because it's built inside, it's an onboard charger. So it's not meant to be a fast charging station, but it was just something that you can plug to the shore. And the power supply had semi-potted, so it was able to withstand the vibration, and it was fanless already for the higher reliability. That's why it was a choice for this customer. And they were actually utilizing the enclosure, the metal frame, for their battery and for their enclosure, which was very heavy metal frames, very thick metal frames that acted as heat sinks for this power supply. So they didn't need to have additional heat dissipation considerations. So next, moving into the controls, right? So we talk about the electrical, the thermal. We want to be able to control these power supplies. And I want to preface by saying that there are analog controls and digital controls available for power supplies as well. So the power supply is not just the black box that provides the electrons to your systems, but they're also becoming smarter and smarter, and you're able to get a lot more useful information from the power supplies. So here are just some common analog control features. And the remote on-off is definitely one of the most important ones, the most utilized ones. So shutting off the power supply, the customer, instead of having to turn on and off the AC breaker, they can utilize the remote on-off feature to turn off the DC side to cut power to their devices. And there are benefits to using this versus AC on-off. Because of the inherent switching mode power supply design, most of the switching power supply designs, when you turn on the AC power, there is a very high peak current instantaneous draw. We call that the inrush current coming from the utility grid. And that can be detrimental to the lifetime of the power supply if the AC is switched on and off very quickly. So the DC on-off is safe and prevents the power supply from that. So again, this is a design consideration a seminar. So my recommendation for you guys, if you guys are designing devices that requires the constant cycling of power, cutting power to your devices or cutting power to certain components, instead of turning on and off the AC power to cut the power, it's a much better practice to implement some form of remote on-off to turn off the DC side, the output side of the power supply. And then there are various alarms that's coming in the form of analog controls. So we typically have DC OK, which tells the system that the DC output is normal. We have AC OK, letting the system know, hey, the AC input is normal. We also have fan fail, as the name suggests, detects the fan's health. And also the temperature alarm also detects if the power supply is over temperature protected or if it's within normal operating temperature. And then for some of the UPS power supplies or inverters, there's also the discharge signals that's also able to let the system know what status, what mode the power supply is running in. And so here's just a quick graph on the output voltage current control function as well, which comes in some of the more advanced power supplies in the form of an analog control. So the user is able to supply an external control voltage, usually between 0 to 5 volt, to the power supply to control its output. And so in this specific case, the output current can be reduced to 20% of the rated output current by giving it a lower voltage signal. So this is good for applications that require dynamic adjustments of power supply output, whether it's voltage modulation or current modulation. This can be especially useful for, like, say, laser, where the output capacity or output power of the laser is directly related to the current that's powering the laser diodes. So we can just by changing the output current of the power supply, the laser manufacturer is able to control the output power for the laser directly. So those were the analog controls. Now I want to talk about the more exciting, the digital controls. So the advantage of digital control, so first of all, is wiring. So for analog controls, because each of them is a separate analog control signal, you need to run separate sets of control wires to each of the power supplies that you want to control those features. For digital control, though, however, most of the digital protocols, they support, you can just have a single bus for the wiring, and then you can wire multiple devices to the same controller. So the wiring is very much simplified, and the distance for the communication controls can also be long. And if you're utilizing modems or products that support remote monitoring features. You can have distance miles or hundreds of miles away, and you can still monitor the status of the power supplies and your system. And which in turn will be able to support higher reliability system designs because it has more robust and more flexible monitoring features for the power supplies. And here are some of the common digital control protocols that's utilized for the power supplies. And the first one is PM bus. So PM bus is based on the I2C protocol, and it is adopted specifically for power management. As the name suggests, power management bus. And the application, of course, is mainly catered towards power supplies or power monitoring and power control applications. And so what it is digital management for power supply outputs and inputs, and it is standardized, which means that the PM bus actually comes with standard commands. So it's universal. There's a set of standard commands so for example, you're acquiring the output voltage, output current, and then the conversion from the digital data to the human language is also universal. So that's the benefit for the PM bus, which has a standardized standardized list of commands that's universal across the manufacturers that adopt the PM bus. And one of the downsides for the PM bus protocol is the shorter communication distance, because it is more susceptible to interferences. And we typically see PM bus used within, like, say, 10 to 15 feet of the controller versus the power supply. And then the next one is CAN bus. So CAN bus is a more widespread, more popular communication protocol across many industries. So some applications include automotive, industrial controls, and aerospace. And power supplies, nowadays, we're also designing them with CAN bus communication features. So CAN bus is able to support high speed and reliability for controls. And it's suitable for more complex real-time controls because it has a higher data rate versus something like Modbus. And however, for CAN bus, there's no universally defined list of commands for power management. So a lot of the commands are manufacturer specified, and of course, if you work with the manufacturers, they will have the list of commands. But then you have to, for your system, you have to design those registers and then to be compatible with those the CAN bus commands that's in the power supplies. And then the benefits for the CAN bus, of course, is higher reliability because it's utilizing differential signal, and it is more resistant to interferences. And we can run distances upwards of 200 feet or even 300 feet for some of the more robust implementations. And it's able to support that longer communication distance. And then the last one we've seen more and more use is Modbus RTU. So Modbus is more common in industrial automation and building automation communications. It is a simple and low-cost implementation, and it's suitable for more like a data acquisition and a set and forget type of control application. So Modbus RTU, because of the limitation on the communication bit rate, it's not suitable for the real-time acquisition application like CAN bus, where you want to adjust on the fly, you want to acquire a lot of feedback data, and then you want to control. So for the Modbus, it's more typically used for setting parameters and setting operating conditions before it is turned on and used running in the field. And again, Modbus is also manufacturer-defined commands for power-specific related control features. So what can digital controls do, right? I introduced you guys about all these communication protocols. So just taking PM bus, for example, and we have the same commands for CAN bus implementations as well because the commands are manufacturer specified. So in terms of read, the controller is able to read the output voltage, output current, the power supply status, if it's in the output mode or if it's in like standby mode. It's able to read the fan speed as well. If it's a smart fan that's integrated with the MCU controller, you're able to access the fan speed. And this is especially important and creative for some applications that can do preventative maintenance. They can monitor the fan speed to see the power supply. If over time they track that the fan speed is increasing, that means the internal components may be degrading and failing over time. So they can set certain thresholds. If the fan speed gets to a certain point, they can perform maintenance on the power supplies, or they can swap out the power supplies. And then you can also access temperatures for temperature controls that's tied to the chips, manufacturing info, the serial numbers, product info. So you can access all kinds of information from power supply. What's more impressive is the writing, so the controls. So you're able to adjust the output voltage, output current on the fly, and you're able to turn on and off the power supplies as well. And for some of the charger applications, what we allow is for the customers to adjust the charging curve. So the power supply can be remotely adjusted to be suitable for different types of batteries if the application is for different devices, different vehicles, or different types of batteries. So, so very, very powerful implementation. It's just what you can think of, right? There's no limitation to the type of information you're able to access if the MCU is able to acquire from the sensor implementations. So yeah. And here's the case sharing where the similar case in the last case sharing where we talk about the customer. This customer was using one of our conduction cooled power supply as an onboard charger. So this specific case is that we also built a fast charger for the customer that is utilizing CAN bus communication to control the charging. So the robot itself actually is intelligent, and the battery's BMS actually communicates with the charger, with our charger, via CAN bus to tell the charger what voltage to output and how much current to charge the batteries. So you're able to control the charging rate, and the battery knows, like if its temperature is below 25 degrees Celsius, it cannot take the full for 400 amp charging current, so it will derate that accordingly, and the power supply will get that message, get that command, and it will only output the required current. So here's an example. And then finally, a little bit about Mingwell. So Mingwell was established in 1982 in Taiwan. So our headquarters is in New Taipei City, and we've established our North America headquarters, North America office in Northern California, Fremont, in 1999. And we have factories all over the world. So our headquarters also is our main, one of the main factories, which performs manufacturing for our high power products. So it's in Taiwan. But for the lower power products and for LED drivers, we manufacture them in China, in Suzhou and in Guangzhou. So we opened our first Suzhou factory in 2006. And 2 years ago, we actually just opened up a new Suzhou Intelligence Park that is much bigger scale and able to supply power supplies worldwide. And so in addition to the overseas factories, I also want to point out that Mingwell, in addition to the Fremont, the California sales office, we also have a smaller operation that's focused on power solution integrations, and it's for value added for power supply related or for power solution needs for the customers. And we actually just opened up this location 2 years ago, and it's in Kansas City, Missouri. Okay. And so now I think we have some time for questions. But if you guys don't have any questions, please feel free to stop by our booth at number 4383 to say hi or to check out some of the latest solutions that we have on display. All right. So thank you everyone for listening in. Do we have any questions or? All right. So again, yeah, thank you everyone for coming. Thank you.